Shanghai is a mega city. With 24 million inhabitants and rising, it's one of the most densely populated cities in the world, with ambition to match.
Shanghai will always be one of the international cities in the world and one of the most important ones in the world.
This global financial center holds 10,000 people per square mile, and the only place left to build is up. In the mid-1990s, development began in an area of farmland on the East Riverbank, known as Pudong.
If you look at Pudong today, 20 years after it is being transformed into an international center for business from a quiet farmland, and today is even dominated with a lot of new high-rise buildings.
In November of 2008, work began on the most impressive of them all. At an astounding 632 meters, the Shanghai Tower will be the second tallest building on Earth, the tallest in China, and one of the tallest ever built in a seismic zone. It will be the most advanced building of its kind on the planet, with 128 floors and 9 indoor gardens, where 16,000 people will work, sleep, and shop, making it a true sky city. And yet, this is one of the most difficult places on Earth to build a skyscraper.
Building a super high-rise building in Shanghai is quite unique because you have to deal with the wind load and also the earthquake load.
For Dennis Poon and his fellow engineers, it's a seemingly impossible challenge.
I cannot believe that today we're designing the tallest building in China and also the second tallest building in the world.
The engineering complications begin at this mighty tower's roots. Because not only is Shanghai an active seismic and typhoon zone, but amazingly, this megacity is sinking into the soft soil below. The land under this massive metropolis is deflating like a giant air mattress, as its shallow water table collapses under the weight of its modern buildings.
For the Shanghai Tower, one of the biggest challenges is the foundation to support this super tall building. With its weight of 850,000 tons, how do you support it in the soft soil condition, which is locally in Shanghai?
The solid bedrock is 200 meters down, with Shanghai itself wallowing on a soft layer of sand, clay, and soil. A geotechnical nightmare ready to swallow an 850,000-ton building like the Shanghai Tower.
So we have to design and build this foundation for the tower to deal with these challenges.
And the engineers only have one shot, as constructing a tower this tall leaves no room for error.
For a super tower, of course, the whole design challenge is to do the foundation right, so you don't have future problems, because you can't fix it later.
The engineers will have to look to the great innovators of the past to defy this seemingly impossible challenge. Once upon a time, the modern world of skyscrapers was inconceivable. Early man was limited by what nature would provide. And for the ancient Egyptians, taller had to mean wider, and an awful lot of manpower. Unless you believe in some of the more otherworldly theories. And when it's come to building towers, the ground below has frequently thrown a spanner in the works.
Mamma mia!
In order to create a skyscraper 11 times taller than Pisa's famous Leaning Tower, the designers of the Shanghai Tower will need to draw on the inspiration of 19th century engineering pioneers. The US city of Chicago is home to one of the world's most iconic skylines. But just over a century ago, engineers were faced with a challenge that meant building any higher than just a few stories above street level was a near impossible dream.
You wouldn't know to look at it, but Chicago is actually one of the least logical places that you could ever attempt to build a skyscraper. We've got soil here that is incredibly squishy. Underneath this kind of shorter, smaller layer of earth, we've got a very, very deep layer of soft, squishy clay. This is a really difficult thing to build a skyscraper on, of course, because when you load the building's going to sink.
As property in downtown Chicago grew ever more valuable and the city began to boom, the need to grow higher and maximize space posed engineers a problem. Taller buildings would mean heavier buildings, and as they had discovered, there was a limit to the weight that the local soil could take.
This is the auditorium building of Roosevelt University, designed by Adler and Sullivan in 1889. It's a national landmark and so important to Chicago as well.
The building is 72 meters high. When it was completed in 1889, it was the tallest building in the city, one that would have been unthinkable just a few years earlier. And the radical innovation that made it possible came from engineer Dankmar Adler.
We're headed down to see Adler's specially designed foundations to deal with the soil here in Chicago.
Previously, the whole weight of a building would bear down on its walls, which would sink into the clay like a cookie cutter. Adler's innovation was to use wood and steel crossbeams encased in concrete to create a reinforced concrete raft that the 110,000-ton building sits on.
I'm going to illustrate what's happening here with this piece of modeling clay used to represent the clay that's under our feet here in Chicago, this sort of peanut butter jelly-like substance. The clay is really quite deep, and the bedrock doesn't start in Chicago until 75 to 100 feet below the surface. So I've got my chopstick here to sort of illustrate, and I take my structure and I go through the hard pan, and they just didn't have the technology in the 1880s and the 1890s to excavate that far down to bedrock. So instead, architects, engineers here in Chicago are coming up with new ways to solve this problem. The method that we're standing on here is sort of the equivalent of this kind of penny that I'm going to illustrate. So this pad or this raft is put down, and then the building, the column on top of that is put on top of that. And you can see that I can push it down a little bit into the clay, but not really that far. This is distributing the load.
Adler's revolutionary engineering solution made building on substandard ground possible. And today, the city's tallest building, the Willis Tower, rises 442 meters, more than 6 times the height of Adler's auditorium. But despite its influence, the auditorium's design wasn't 100% perfect.
So on the north edge of the building, we've got this large, heavy exterior walls that are much heavier than what's happening on the interior of the building. And we can see the challenge with that, the fact that this is much heavier and this is much lighter in the building with this long crack here in the floor. And we can also illustrate that pretty well with these marbles.
Although the Shanghai Tower would be impossible without the innovation of reinforced concrete raft foundations, its engineers cannot afford for it to subside like the 19th century Chicago auditorium.
If the building does not settle uniformly, it will tilt. This is something we cannot afford and we don't want to see. Because the building is so tall, a slight tilting will cause a big deflection on the top.
To overcome this potentially catastrophic risk, the engineers will have to take Adler's ideas and supersize them. In 2008, a 2-year operation to build the foundations begins. First, they sink hundreds of deep supporting piles into the soil, then begin pouring the raft or mat foundation.
Construction of the mat foundation so deep below grade is a big challenge.
It takes a world record 60 hours of continuous pouring to create the mat, a process involving 2,000 workers and 450 concrete trucks.
We basically use almost all the concrete trucks in Shanghai, and finally we overcome this challenge.
All in all, the mat soaks up 61,000 cubic meters of concrete. Another world record.
61,000 cubic meter is a lot of concrete, and comparable to the Hoover Dam many years ago in the States.
Without the pioneering work of engineers like Dankmar Adler, building a tower this high in Shanghai would have been an impossible dream.
You can see the sheer scale of this tower, and you can imagine how big the foundation we need to support this tower in a soft soil condition. And we get it done right, look. I even cannot believe it.
But in creating this ultra-modern skyscraper, its builders still face major challenges. And will have to draw on innovations from the past.
This is arguably the world's first skyscraper.
To produce more impossible engineering. Begun in 2008, the Shanghai Tower will be the most advanced skyscraper in the world. The tallest building in China and the tallest ever built in a seismic zone.
It is a fantastic piece of engineering. We are all grateful that we have the opportunity to work on this iconic project.
The tower is a massive 632 meters tall and will consist of 128 stories of cutting-edge engineering and contain gardens, shops, hotel, office space and residential accommodation.
Actually to build it and also overcome many engineering challenges. It's still, to me, it's quite incredible and unbelievable.
But in creating a building this immense, the architects and engineers have set themselves a seemingly impossible challenge. Each floor weighs an average of 6,500 tons, making the building enormously heavy. The structure itself has to support a total of 850,000 tons.
For a super tall building, you have enormous forces to support. We're not building a house, we're building a 128-story building, the second tallest building in the world.
It's a challenge that would have been impossible if today's engineers weren't able to draw on the great innovators from history. Once upon a time, the maximum height of a building was determined by the thickness of its walls, because the weight of each story had to be supported by the floors below. It meant tall buildings remained the realm of the rich and powerful. Medieval religious architects enabled thinner walls and large stained glass windows by using external supports called flying buttresses. But these also made buildings grow sideways and were still the preserve of the wealthy church.
Bless you, my child.
But there was a revolution on the horizon. And this seemingly innocuous and picturesque region surrounding the River Severn in England was the crucible of it all. Shropshire was at the heart of the Industrial Revolution, the Silicon Valley of the 18th and 19th century. Its engineers were at the very cutting edge of technology because they had mastered the production of iron.
This area gave birth to some of the greatest engineering pioneers of our time and enabled the construction of iconic structures like this Iron Bridge, the first cast iron bridge of its kind in the world.
But just a few miles upriver is a somewhat less iconic, but arguably much more significant building.
It wasn't until about 20 years ago that the historical importance of this building was properly understood, which is why it's fallen into disrepair.
This crumbling red-bricked mill is one of the most important buildings in the world.
This incredible but rather sad and dilapidated building in Shrewsbury is arguably the world's first skyscraper. It's the first time that iron was used in a multi-story frame construction, and it really paved the way for tower blocks and skyscrapers that we know today.
Built in 1796, Ditherington Flax Mill was the brainchild of engineer Charles Babbage. And he drew on the region's groundbreaking use of iron to build the first metal-framed building on the planet.
Previous to the iron frame, the taller the building, the thicker the walls had to be to support them. But with Babbage's design, the walls could be thinner, which meant that the rooms could be much larger. It also meant that you could design buildings much taller.
In Babbage's design, all the weight of the building was borne on its iron frame. So none of the walls were load-bearing, making the sky the limit for the first time.
This main building had 5 floors, including this attic, which was previously unheard of. It had a working area of over 2,800 square meters, or 31,000 square feet. And these narrow, relatively lightweight metal beams would be able to support much more weight than the solid brick walls of previous buildings.
This simple but brilliant engineering solution meant that Babbage's flax mill was the forerunner of almost every large-scale building in the modern world.
What Babbage achieved in this building was truly remarkable.
In building the Shanghai Tower, its engineers are employing the same principles as Charles Babbage's 5-floor flax mill, but on a whole new scale. The 128-story building, however, will have a steel frame instead of iron.
The advantage of structural steel is it's lightweight, it's high strength, and easy to erect, and can be prefabricated in the shop with better quality control.
Because the steel bears the weight of the structure, the external walls no longer need to be load-bearing. They don't even need to be flat or straight. They can be made from a variety of lightweight materials, such as glass. And architects can mold them into any shape they want to express their vision. Zheng Xia was one of the lead designers on the project.
When you on the city looking at this building, different view you look at, the building looks different shape. The movement looks different. You feel like it's alive, something alive organism, you know, because it's don't feel like it's a dead, just a cold object.
The whole building is clad in a series of glass walls, each of which can be suspended over many floors like a giant curtain, thanks to the strength of the steel rods that hold them in place.
We're at the top of the 101st floor building, and you can see the curtain wall is being hung 14 floors above us.
Between the curtain wall and the inner core, which houses offices and hotel rooms, the designers have allowed the building to breathe, creating a massive open atrium, only possible because of the building's lattice-like steel frame.
Here we are standing on the 8th floor of the building. You don't want to block too much sunlight to a massive structure. It opens up the airy feeling.
Yet despite the use of super lightweight materials, the Shanghai Tower weighs in at a staggering 850,000 tons. With 24 million inhabitants, Shanghai is one of the most densely populated cities on Earth. And the only way of expanding its globally important financial center is to reach for the skies. 632 meters tall, the Shanghai Tower is being built as a living city in the clouds. It will house offices, shops and hotel rooms, as well as conference and concert halls.
If we turn this building down, it's going to be 600 meters long, about 6 urban blocks. So in a way, we think each of this zone is a communities.
But in creating a super tower in which 16,000 daily users will work, rest and play, its designers have set themselves a lofty challenge: how to transport its population around this massive structure.
Who wants to come up to a 100-story building and work up there? I can see many office buildings with a huge crowd in the lobby.
It's an engineering feat that would be impossible without one of history's great innovators. By the mid-19th century, the world's skylines were still relatively skyscraper-free. For one reason, no one wanted to take the stairs. Unlike the penthouses of today, the higher you lived, the poorer you were.
Mustn't grumble.
Steam-powered and hydraulic lifts were being used in mines and factories for freight, but they were too dangerous for people. The ropes on the pulley system were inclined to break. But city skylines were about to change. Thanks to a man named Elisha Otis, in 1852, he came up with an idea that revolutionized the world of construction, pioneering a simple mechanism that changed the way we use tall buildings forever.
So we're here in Bristol, Connecticut at the Otis Elevator Company test facility. This is where they test the newest elevators that they're going to install in buildings across the world. But they also have this replica of a device that Elisha Otis first constructed for the Crystal Palace exhibition, the World's Fair that ran from 1853 to 1854.
The World's Fair was the perfect shop window for Otis, who was a showman as well as an inventor. He knew that the eyes of the world would be upon him if he could prove that his idea for protecting passengers was safe as well as practical.
So I think it's important to remember that Otis didn't invent the elevator. Certainly there had been ways of moving goods and people up and down from floor to floor using hoists and pulleys for centuries. But what Otis did do was to recognize that people were afraid of going into an elevator. So at the 1853-1854 World's Fair, he builds this device to provide a brake, a safety, in case the rope broke.
With his showman's hat on, Otis decided the best way to prove his idea was to put it to the test, using himself as a guinea pig. In front of an expectant audience, he stepped onto the platform, rose above the crowd, and gave the signal for the rope to be cut, a potentially fatal step.
So let's see if Mr. Otis's invention still works. Ready whenever you are, Rich.
The system features a wagon spring, which is held up by a rope which keeps it in a state of constant tension. When the rope is cut, the tension in the spring is released, which causes pins fixed to the side of the spring to lock into a ratchet located in the wooden frame. This brings the elevator to a complete stop, preventing it from falling and injuring any passengers.
And all these years later, every single elevator today around the world has a similar safety device that is allowing passengers to feel safe in tall buildings. And I didn't plunge to my death.
Otis's invention transformed the world's skylines, and cities like New York that couldn't expand sideways could now reach for the skies. Fittingly, in 1913, it was the Otis Company that were commissioned to provide the lifts for one of New York's most iconic skyscrapers, the Woolworth Building.
By 1916, more than 100,000 people had paid their 50 cents to ride the elevator to the observation deck at the top. And now, 100 years later, those original Otis elevators are still being used to carry office workers up and down.
Otis's invention meant that instead of the poor being consigned to the building's upper levels, the value of floor space now increased as you went higher. Penthouse living was what everyone dreamed of.
As we drive through New York, it's easy to forget, I think, that within just a short span of time, just about 160 years, all of these skyscrapers have been constructed. And so the rise of the elevator and the rise of the skyscraper are so closely linked.
Otis's first passenger elevator travelled at 0.2 meters per second. At that speed, it would have taken nearly an hour to reach the top of the Shanghai Tower.
Look at outside. We are more than 100 stories above ground. You can see the magnificent view. For this tower, we are using the world's fastest elevator traveling at 18 meters per second, which is faster than the speed of a car traveling at normal cruising speed.
In all, the tower has 106 elevators, single and double deckers, including the world's furthest travelling single elevator at 578.5 meters. And along with the residents, shoppers and office workers, will transport thousands of tourists to its top floor observation deck.
We are on the street level right now. You see this 128-story building. The view at the top of the Shanghai Tower will be unique. And when it's all done with the elevators, you can get up from the ground floor to the top up there in 35 seconds. Marvelous.
The Shanghai Tower's 632-meter elevation won't only provide stunning views of the metropolis below, it will also present a massive obstacle to the wind. Shanghai is in a typhoon zone, and defending the tallest building in China from the immensely powerful and potentially devastating winds that sweep through the city is a major challenge to the engineers.
On the 100th floor, the wind load can be up to 94 pounds per square foot, which is almost 4 kPa. So it's a huge wind pressure. How do we resist this wind pressure?
Creating this giant piece of engineering would be impossible without the great innovators of the past. The first wind tunnel was constructed in 1871, a full 30 years before the Wright brothers' inaugural powered flight. But they had always been very much geared to aeronautical engineering. That was until brilliant engineer Jack E. Seismic evolved the technology to enable the world's skylines to grow ever higher.
In the late 1950s, Seismic and his contemporaries pioneered the use of new wind tunnels.
Professor Rhys Morgan is visiting wind engineering firm RWDI, who have drawn on Jack Seismic's innovations, which included much bigger tunnels than for aeronautics and used irregular shapes to mimic the unpredictable winds that can hit cityscapes.
Blocks like these on the floor create the kind of turbulent atmosphere, the turbulent winds that you see in cities and urban environments. So they're perfect for testing structures that we want to build in cities.
One of the early skyscrapers to be tested in Seismic's wind tunnel was New York's World Trade Center, then the world's tallest structure. The innovations that resulted feed into the design of every new skyscraper, including the Shanghai Tower. A scale model is being placed into a mock-up of the London skyline to demonstrate how wind can dangerously affect tall buildings.
Wow, it's really windy.
As the wind rushes past the structure, it forms into eddies of low pressure on either side.
So the wind is coming in here, it's hitting the side, and then as it comes around the corner, it produces a low pressure region here. And that causes the building to move this way. But then that means that the wind coming around this end starts to cause a little bit of movement this side and low pressure. So we start to get this low pressure, low pressure, low pressure, low pressure, and that causes this oscillation back and forth. This is just amazing. This is kind of, this is real engineering happening here. That's moving a good 5 centimeters either side. I wouldn't want to be on the top of this building if it was a real building in the city.
For architects like those that designed the Shanghai Tower, the challenge is to come up with a shape that reduces those vortices.
Okay, let's try this one.
This time, the building is tapered like an elongated pyramid.
And you can see there's very, very little movement. Let's turn it up a bit more. We're running at 3 times the wind speed of that very first model that we saw. and the building's just not moving anything like as violently.
Because of the tapered shape of the building, the wind creates vortices of different sizes at different heights.
It's causing some oscillations down here, but they're much slower than the oscillations occurring at the top end.
That means that different parts of the building are trying to shake at different rates, with the net result, in this case, that they cancel each other out.
And so it prevents the building from oscillating quite so violently.
Jack Cermak's invention has allowed city skylines around the world to change radically. Today, no one would think of building a skyscraper without first testing it in a wind tunnel. The Shanghai Tower is tapered, but it also has a distinctive twist, which is directly influenced by tests like this. The design reduces wind loads on the building by 24%.
The twisting of the building is a great example for engineers that can combine creative architectural design with good engineering when we work together in tandem with each other.
The architects also designed a notched V running the entire length of the spiral.
Number one, if the building is continuous spiral without this V, you don't understand the spiral as much. Once you have this break of the V, you can actually read the building moves, the spiral shape, much better, clearly. Number two, we actually make this as an entry to the office zone. So it's very visible, very easy to remember, right? People don't get lost. Then number three, eventually, we make this all LED graphic. So it's like a river runs through it. It's very, very cool.
The notched V-shape started out as an architectural flourish. But when they tested it in the wind tunnel, the designers of the Shanghai Tower made a discovery as welcome as it was unexpected.
This notch also helps to cut down the turbulence effect or the vortex shedding of the building. So the tapering shape of the building helps the aerodynamic, the twisting helps, and the notch helps. And at the same time, the tapering also lowers the center of gravity of the building. That gives us more stability. The lower the center of gravity, the more stable the building is.
Started in 2008, the Shanghai Tower will be the most advanced skyscraper in the world. And the tallest building in China. And in creating this record-breaking super tower, its engineers are having to overcome seemingly impossible challenges. But the Shanghai Tower faces another potentially devastating natural phenomenon. Shanghai is in a level 3 seismic zone.
Shanghai Tower is the second tallest building in the world. Of course, we're not only designing this building for typhoon wind load up to 120 miles per hour wind load, we also have to design it for significant and severe earthquake.
To overcome the challenge, its engineers will have to look to history's great innovators. Earthquakes are among the most powerful of all natural disasters, leveling buildings and triggering tsunamis. Neighboring Japan is the most seismically active country on Earth. For years, no one could understand why regular buildings would collapse in earthquakes, while traditional pagodas stayed standing.
この五重塔、当時の五重塔は高さ51メートルですね。日本で一番高い五重塔です。それがこのように約400年間大きな地震、それから強い台風に耐えてきました。これ本当に素晴らしいことだと思います。
Modern studies of pagoda design eventually revealed the secret.
まず第一に非常に柔らかい構造ですよね。多くのジョイントがあって、それから食い物もありますし、柔らかい構造なんですね。ですから、地震が来ると、スネークダンス説というそういう説を唱えた先生もいますけれども、要するに蛇がこうね歩くように、そういうような例えで強度を示すことがありますけれども、くねくねとこう強度をする。
Pagodas are typically 5 floors high, but each floor is capable of moving independently, so when a quake strikes, its snake-like pattern keeps the center of gravity more upright than a rigid building would. The wooden joints that support each floor consist of several separate components, so each part can slide and move, and the friction they create acts like a damper to soften that movement.
この接合部が多くの接合部がところでエネルギーをですね吸収するというシステムを持っているわけです。
The whole of the Shanghai Tower has a very similar template to that of a pagoda. The structure is divided into 9 vertical zones around a central composite steel and concrete core. Huge perimeter columns and outriggers are also fixed to the central core to further brace the tower against natural disasters.
The core is just like the main trunk of your body, and the 2 column, the exterior column outside is like the ski post. And this steel truss member is connecting your body and the column, giving you a much better stability for the building to resist earthquake.
The earthquake-proofing measures extend from the base of the tower right to its tip.
Here we are, coming up to the 125th floor of the tower, which is one of the most important rooms in the building.
So what is it that makes this such a key part of the structure? The answer is suspended above Dennis's head.
You can see we have a 1,200 tons of steel block being hung 4 stories above us.
So why would engineers take up valuable floors and sacrifice the revenue they could generate with a steel block the weight of 600 family saloon cars? Boston's John Hancock Tower, 60 stories high, was completed in 1976. Its then futuristic glass-clad design anticipated the skyscrapers we know today. When it first opened, upper floor occupants complained of motion sickness as the building swayed in the wind. This came to the attention of an engineer, William Le Mesurier, who came up with an ingenious solution.
What I've got here is a very simple model of a skyscraper. It's a beam structure going up several stories.
Turning a handle at the base of the structure mimics an earthquake.
With steel-structured buildings and glass buildings, of course, we're reducing the weight of those buildings, so you can actually go much taller, you can build them much taller. But then you do have this problem with sway.
Le Mesurier's genius was to find a way of counteracting and cancelling out the swaying of the John Hancock Tower. He took over the 58th floor and installed 2 steel boxes, each filled with several hundred tons of lead and resting on a steel plate.
You have to imagine this is an 800-ton weight that I'm lifting up onto my skyscraper now, and I'm just going to tie it to the top of my structure.
The tuned mass damper, or TMD as it became known, had a dramatic effect.
It's amazing. The structure is hardly moving. I mean, it's quite phenomenal. So what we're seeing here is the mass damper oscillating out of phase with the vibration of the structure. In a building like this, you wouldn't have an 800-ton ball flying around violently and smashing into the walls and things.
The principle is simple. As the building sways one way, it pulls the damper with it. As the building starts to sway back, the damper is still travelling in the opposite direction, so it stops the building from going too far.
It's amazing how much of an impact it has. It really does just stop the structure from swaying around. Without tuned mass dampers today, we just wouldn't have any of the kind of mega structures that we have.
As buildings have got taller, so the dampers have got bigger.
We are walking to the upper portion of the TMD system, 2 mass damper system. Without this 2 mass damper, we have to use a lot more structural steel and material to stiffen up the building.
So despite taking up 5 of the tower's 128 floors and weighing over 1,000 tons, it actually made the building cheaper and lighter to construct. It's taken 15 years of planning, design and testing, and 7 years of construction to raise this super tower from its foundations deep in the Shanghai soil to the tip of its 128th floor. But by drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own, the engineers, designers, and workers on the Shanghai Tower have overcome substandard ground, high winds, and earthquake risks, and succeeded in making the impossible possible.
Look at this super tower, 632 meters tall. It is exceeding my expectation and a lot of people's expectations.